In order to connect Young's modulus to the inner atomic spring constant, we need the initial formula. Stress over strain is equal to Young's modulus, where stress is the force total over area, and strain is delta L over L. First, we're going to deal with the strain portion of the formula. Delta L represents the distance a spring is stretched or compressed, and L is the length of a spring at a relaxed state. With that in mind, we have these two values, and we can take any pure metal, so it could be copper or nickel, whatever, and we can look at it on an atomic level. Each box represents one atom, and each atom has a diameter of d, and because it's all the same atoms, the diameter doesn't change. Also, there is an interatomic bond that works similar to a spring, and that's what we're going to be looking at. And the spring, the length of the spring is also d, because when you combine the radius of one atom with the radius of a different atom, that is all part of the same, or is all the same element, it is equal to one diameter. This leads to our final formula, rewritten formula for strain, which would be delta L over L equals S over D, where S is the amount a single interatomic spring is, or bond, is stretched or compressed, and D is the total length of the spring, which we discovered is just the diameter of one spring. For stress, we have the initial values force total over the cross-sectional area of a spring. If we want to break it down to an interatomic spring, we know that force is equal to a spring constant of any type of spring. In this case, it's the spring connecting two atoms multiplied by the distance it is changed when it's compressed or stretched. To find area, we can just break it down into length multiplied by width, because we're dealing with cubes here, and since we know the side of one cube, we know it all, and we know that each little side is the d, or the diameter of the atom, and we can multiply one side by the other to get the total area, which is d squared. If we're looking at the area of an actual spring and not on the atomic level, it would be just the area formula for a circle. With all of this broken down, we can rewrite the formula as force total over area is equal to Ks, which K is the spring constant, S is the distance it's changed when compressed or stretched, and d squared is the area, and that's equal to stress. Circling back to the original formula for Young's modulus, we have this right here, this whole quotient, and if we rewrite it into the values that we have found, we get Ks over d squared over S over d, and we just divide them. You can cross multiply, or you just multiply by the reciprocal of the bottom one, and when you do that, the two d's cancel and you're left with 1, and the two s's cancel, you're left with 1d, and that gives you your final formula of k over d. So therefore, Young's modulus is equal to the interatomic spring constant divided by the diameter of an atom, and that's how you can connect Young's modulus for normal springs to the interatomic spring.